Hi guys, and welcome to this video. Today's video will be a little bit different than the videos that I usually do, but I just saw Pavel's video that came out a couple of hours ago, about 4 or 5 hours ago, and I wanted to do a response to his video because I think there are some things that he is not really taking into account, and I think he's making the wrong conclusions, and I don't think that whatever changes he intends to make as a result of this will actually contribute positively. So this is kind of a response video commentary on his recent video about the 3D printed airboat that wanted to dive. And yeah, so let's have a quick look at what his reasoning is on what went wrong. And then I will tell you what actually went wrong and give you a couple of examples that you can even try yourself to verify that what I'm telling you is correct. Okay, so let's have a quick look at the video and then we'll go into the details.
As you can see, it was a failure. And it was a failure due to several reasons. The reason number one, this was the miserable failure, is because there was not enough of the buoyancy. The 3D printed hull, although it was printed from the lightweight PLA, had not enough of the buoyancy to support the weight of the battery, motor, servos and everything. It was
Right, all right, I'm just gonna go back to this. Okay, I'm gonna go back to this because I'll need this image in a bit, and I also want to have a look at the other images that we saw. But first of all, what we'll do now is we will take paint and just draw the sections longitudinally and transversely for the boat that Pavel had. All right, so this was the longitudinal section, roughly speaking. All right, I can't know exactly what his profile looked like, but roughly from what I could see, it was something like this. All right, and then the back part was just straight and straight down at the back like that. Then he had a place where he mounted his motor, something like this. There's the motor, roughly, of course, and this is the prop. Okay, and then he also had the last thing that he had was a fin at the back, something like that, right? So this was connected to a servo in order to actually make the whole thing maneuverable, right? Okay, so first of all, we did this. Now the second section that I'd like to do is a section somewhere around here, okay? Because it doesn't change much at the front. It only tapers down, as you can see here. So let's do another section. Try and make it as scale as possible. Something like this, because it was quite square. And let's choose the right color. And then we had something like this, roughly, and that was kind of bent inwards. And the same, oops, that's not supposed to happen. Let's try that again. So something like that, and then bent inward. And then the same thing on the other side. Roughly like this, and then bent inwards, right? And obviously you can finish that off with a flat line at the bottom. Something like this, all right? So this is the section that we saw. And obviously I'm not going to draw the motor and all that. It's not really that important for this section, but this is what we had, okay? Now, I'd like you to do an experiment. Go to your kitchen sink and take a spoon and hold it upside down, let the water run, and then hold the spoon right next to the water flow. What's going to happen? Try it. Pause the video here, go and try it, have a look, and see what will happen, okay? Because the next part will be all about that, okay? If you pause the video and you're back, then let me explain what's going on. All right. This front part is a bit shaped like a spoon. Obviously, the curvature of the spoon is very different and so on and so forth, but it has a curvature. Okay. So the first thing, before looking any further into eccentricities, thrust lines, etc., etc., let's look at the shape of this front and how water flow was behaving both in the video as well as on your spoon. Because if you remember from testing this out, you may have noticed that the water was kind of hugging the spoon, right? It was, by the way, I should have told you that you should hold the back of the spoon towards the water flow. Maybe I forgot to say that, but anyway, I hope you tried both sides, because in both sides you will notice something, okay? And that is that if you are holding the back of the spoon towards the water flow and you let it in the water flow, it will suddenly drag it inwards even further. And you can even start to tilt the top of the spoon away from the water flow. And the faster the water flow, the more it will be sucked in. Okay? And that is because of how non-compressible fluids behave. Okay? So when we have, so there were two things that we could see, and one thing that we can definitely visualize in this section, which is how the water flow was behaving that was coming from the front. Okay? So the first thing that we noticed is we had water flow that was turning itself back around and going towards the front. And then we had obviously some of the water flow which was going underneath. But then we also, if we were to do a finite element fluid model, what we would see is that this water flow is something like that, okay? Like the directional lines of the water flow will be something like this. I don't have a fluid dynamic software installed because those are extremely expensive. And I'm not going to install one because I know how it looks like, okay? And it looks exactly like this, okay? We have a pocket which has almost static fluid, okay? It's not really static, but it's almost like it is static. And then we have some fluid which is being pushed out the bottom and under the, so like that. And then we have fluid which is being pushed up, right? And it's going up like that. If you try with your spoon, you might notice this as well, because if you change the angle of the spoon, not only will it pull the spoon inwards, but you might see some water coming in the opposite direction, right? It's almost like water going back up, okay? And this is because water is actually relatively sticky, okay? When you think about it, it's not a fluid that can exhibit laminar flow and like separation. It cannot separate off from a surface. It has to stick to a surface. So what ends up happening in Pawel's case is this backside, as this is tilting forward, right? We've noticed that it tilts inwards. As it tilts inwards, this backside actually tilts upwards, right? So what actually happens, if we draw this just inverted and at a slight angle, we actually get something like this. Okay? Something like that. And if I draw a straight line from this point to this point, I think you can see what this resembles, right? This resembles the airfoil section of a wing. And as everybody knows, lift is generated approximately here. Well, in water, we don't have lift as such because lift is generated by high velocity, low pressure airflow. And we don't necessarily have that in this case. But if you tried something similar to this, and let's say you took a flat water bottle, fill up your bathtub, and then drag the water bottle across the surface, you'll notice how the water bottle will start to dig itself in. I call it digging. Obviously, we're not digging. It's not soil, it's water. But it's almost like it's digging itself into the water as you're moving it across. And the reason for why that is because still this fluid tries, as it's going around, I'll draw it in blue, as it's going around, it needs to, it almost creates a kind of like a suction at the bottom, okay? Because it can't go any other way apart from the bottom. And so it tries to escape the bottom by moving faster towards the back, and thereby, by increasing the velocity, it actually manages to stick better to the bottom, to the underside of the boat, right? And as you could see, this boat is quite flat, so obviously it has a nice flat surface to stick to. We have nothing that can actually separate the water from the boundary, right? From the boundary layer, from where it's stuck to, okay? So that is issue number one. And then as this is happening, there's a secondary effect happening. Obviously, as this water is going forward, it is exerting drag onto the surface, right? But it's not just going forwards and tumbling. It's now kind of digging the nose even further because it's tumbling forwards like this, right? It creates like a little vortex. And this vortex is actually bringing the nose even further down up to the point where the water level reaches the nose, and then a tiny little wave just manages to splash onto the top. And because it's not all perfectly watertight, it eventually enters the hull of his boat, thereby reducing the buoyancy. Okay? Buoyancy is an important factor, and the simplest explanation for buoyancy is an object is buoyant when the volume of water that it displaces and the weight of that volume is it's positively buoyant when the weight of the volume that it has displaced is greater than the weight of the whole object when it is underwater, right? But what is happening now is that because we have started to lower this front, but we have a much narrower section, right? Like this section, obviously, if we took a section, right? If we say we took a section right there, then obviously this shape would look more like this, right? So now we've brought in a section into the water that has less air, whilst raising a section out of the water that contains more air, making it even less buoyant, right? That is a tertiary effect to all of this. But let's not go that deep. Let's actually look at another thing which is a great contributor in this. Obviously, to discuss how much it has actually contributed, we would need to run some kind of an analysis, right? It's not possible for me to tell you, okay, it contributed 20%. It's not possible. But I can give you an estimate and say the water itself and the shape of the boat has contributed maybe more than 50%. And then the remaining percentages are kind of divided up into different parts, but one of the major ones is this one here. And that is the thrust. So we know that this prop is blowing out air in that direction, meaning that it's pushing in this direction, okay? So therefore, like basically this, the force on this holder, on this prop mount is actually pushing, it's being pushed forwards, being pulled forwards. If we had a pusher prop, it would be the same thing. It doesn't matter because essentially it only matters where the airflow is directed to. So the equal and opposite force is this one here. And then if we say that our CG is somewhere here along this line, then essentially we have an eccentricity, okay? So that is a moment. Now that we have an eccentricity, that is a moment that is going around this eccentricity. And it doesn't actually matter where this eccentricity, where the CG is of the boat, because the eccentricity is always the same. It's where the line of thrust is perpendicular to the CG, okay? So speedboats or any kind of a boat has a correction for this, because obviously in a normal boat where you have the prop at the bottom, somewhere here, for example, your line of thrust is here. But what speedboats can do is they can actually vary the pitch of this, right? They can angle the motor upwards, or they can angle the motor downwards, and thereby angling the pitch downwards. So this is another topic, and we'll have a look at some images online of this. But the eccentricity of the prop combined with this effect here and what's happening at the front, as well as the fact that this is being pulled in, it's almost like it's digging itself in. These are the two main contributing factors. And now, if we think about how we can improve this, there's quite a few obvious solutions, okay? So the first part is don't make the front flat, okay? That is a recipe for disaster. What we're trying to do is we're trying to push the water out of the way, and we're trying to pull the front out of the water. The more that we can pull the front out of the water, and the more we can pull the whole boat out of the water, the less contact it makes with the water, the less resistance it has from the water, the less drag, essentially. And the less drag, the faster it will go. And so it's like a positive feedback loop that is limited by the amount of power that we can put into the system. So of course, there will be a point when the forces will come into equilibrium, where the power that's coming out from the prop versus the energy that is required to push the water away and counteract the drag and so on and so forth is equal. And that's when we will reach a stable equilibrium where the boat will not either accelerate or decelerate. We can also see in the video that he was showing that the boat was going sometimes a bit faster, sometimes a bit slower, and it all depended on what angle it was at. And this was one of the reasons why, because we were varying the resistance that the water was having on the boat. Okay, so what we'd want is we'd want the nose, or I don't know what it's called, I don't know the boat terminologies of this, but I'm going to draw it up in red so you can see it. We'd want the nose to be nice and pointed, and then so that would be basically if you had to take a section along here like that and just like look into that direction and upwards, it would be nice and flat. And then sorry, not flat, but nice and pointy. So definitely not flat. Sorry about that. And then as we're moving out to the following sections, we would have something like this. Okay, we'd have something like that, and then something like that on the other side, right? Something like this. Okay, because this will actually help us to not only cut through the water, but also to push the water in the correct direction. And what I mean by push the water in the correct direction is this. When the boat is moving, obviously it's cutting through the water, but part of the water is also being directed outwards, right? It's being directed into this direction. So rather than it being directed forwards, it's being directed partially forwards, but also more towards the side, right? This is why speedboats tend to be very long rather than being very short and having a very shallow angle. What I mean by angle is basically the angle between the oncoming water and the tapering of this, right? Because this tapers as it goes back, right? Most likely it's actually not going to taper like this. It's more likely to taper like that, almost like a bullet shape, like a dome. And then the center line obviously is here. And so if I drew the height lines, it would be something like this, right? Where the bottom stays, and then maybe at some point it becomes actually flat. So for example, this is where it's flat. This could be a section like this, right? If you wanted to have a flat section, but then the rest of it would actually all be tapered. And we'll have a look at some pictures online, but let me go back a few steps before we rush into that. And you know, this is just to summarize. So we've got the effects of the water. We've got this front section being pulled down, and by being pulled down, it goes on. The water manages to go on top and also fill in on the inside. And because of the fact that we are going down, all the water, as this is tilting, all the water manages to accumulate over here, further exacerbating the whole effect, right? So we've created like a negative feedback loop in order to sink this boat rather than to make it float. Now, there are a couple of tricks that we can do in order to prevent that from happening. And you'll see this in many speedboats and toy speedboats and, professional speedboats. And that is, we introduce a flow separation point. Okay, so it looks something like this, and some of you may have seen this, but it looks a bit like that. And the reason why these notches exist, sometimes they try to keep the notches inside of the fuselage, sometimes, well, the fuselage, the hull of the boat, sometimes the notches are on the outside. It doesn't really matter where you put them that much, as long as they're there, because the objective is to introduce cavitation, right? Because the water that's going around here, it can obviously not take a 90-degree angle. It's obviously, it has some velocity. So if we think that the boat is static and the water has velocity, the water would have a relative velocity. So it can't just enter this cavity. And so it creates a cavity. And by creating a cavity, we have actually managed to reduce the amount of area that we are making contact with the water. And if we manage to reduce the amount of area that we're making in contact with the water, then we have also reduced the drag that we're experiencing from this water. Obviously, we can do this all around. So this is not just shown at the bottom. It also can exist on the sides, right? It can go all the way across like that, either going inwards or outwards. In both cases, the most important thing is that it's actually separating. Now, obviously, pushing it out, it will try to come back in. So what most boats do is actually they have something like this that goes inwards a bit like that, and then cuts out this section. Sorry, other way around. It cuts out like this, and then goes in like that. Okay, so a bit like this. Yeah. So it has the same effect of the water being separated at this point, a cavitation being introduced, thereby lowering the surface area. So rather than having this additional surface area here, we have now only got the remaining surface area, all the way up to the end, and obviously whatever we have in contact with the front. Okay, so this is a nice little trick that you can introduce. And of course, if you wanted to test this and you wanted to make it variable, you wouldn't have to reprint all of this. You would just maybe have to print this part, and then you can stick it on with some double-sided tape, try it, see if it works, see what effect it has, and if it has a good effect and you're happy with it, then you can actually take this and actually move it inwards and have the same effect. Okay, that's trick number one. Okay, trick number two would be to obviously take the prop, lower it as much as possible. Now in the video I wasn't able to see how low his prop was. Maybe the prop was already as low as possible with only a little bit of tolerance to make sure that the blades are not touching in any way. And that's okay. If he's already done that, then I have nothing to worry about from this side of things. So we've got our motor somewhere here, let's say, roughly like that. Then obviously we have nothing to worry about. And the final advice that I'd like to give to Pawel would be to use a product called plastic dip. Many of you who are driving cars may have come across this. It's called plastic dip. That is the name of the product. Essentially what it is a sprayable rubber that as it dries turns into a nice ductile rubber surface. If you look at some of the pictures of how it looks, you see it comes off from a smooth surface. You can literally peel it off, right? Obviously, since he's using lightweight PLA, you can still use lightweight PLA. It's not a problem, so long as he saturates the lightweight PLA to such a level that this rubber creates a nice seal, right? And another thing that I would say is, you see this hatch on top, it's not secured by anything. Now, you have to imagine that if you seal something from the outside, you've also sealed the inside. And what is more likely than not to happen is, if let's say you seal all of this around, right? So you've sealed the inside and you've created like a rubber on rubber joint, and that is creating a nice pressure fit, then one of the issues that you might be having is you might be having a high pressure buildup because your battery is getting warm, your ESC is getting warm, thereby the air is getting warm and the air is expanding. So essentially you're creating a higher pressure on the inside compared to the outside, and that could lead to the lid just like popping off, and then obviously it's not creating a nice tight seal. So what I would recommend is if he uses something like this, which essentially there is no problem in doing so, but it would be a good idea to possibly take some thumb screws and have like two thumb screws in either of the four corners, in all of the four corners like that. And then what that will do as you're screwing in these thumb screws, you're basically preventing that lid from coming off no matter what pressure you have. Alternatively, if you want it to be a pressure fit, or you want to have a little bit of a, almost like a little lip that goes around, so it would look like this, a bit like that, and then the outside is a smaller dimension than the inside. So essentially, that's your lid right here. That is basically looking at, for example, this internal wall here. So obviously you've created a pressure fit, and this fits great. And now all you need is to have a little bit of a vent hole. You can do this with a straw, for example. So I have something like that, somewhere at the back where it's clear from anything, and it's above. Obviously, it's above the water line, safely above the water line. And then what that will ensure is that any pressure buildup that you might have on the inside of this, all that pressure can escape through the hole, right? And many RC boats have things like this to ensure that pressure can be equalized, or they're being cooled internally or whatever. But they do have some way of venting, right? Because if you have high pressure buildup, then essentially you're just creating more and more trouble for yourself. If we just have a quick look at some speedboat designs, so um, speedboat, right? We can see quite clearly this little notch that I explained. And the purpose of this notch is obviously to separate the water flow at this location so that this part can just hover above the water, right? And the only thing that is actually pushing this further forward is actually that. Now, if we look at some conventional boat designs, we can also see that the boats have a slightly irregular shaped front, right? So not only is it pointy on the front edge, but also we have these ridges along the sides. And the reason why these ridges exist is to essentially try and force the water to create a wave that tumbles outwards, right? That is the whole purpose of this. You can even see that the bottom part of this boat is even further lower than the back part, right? And the reason why is because we're actually trying to push this out of the way. Now, some boats have ridges that run perfectly linear, but actually when you look at them, due to the curvature of the boat and so on and so forth, they do behave slightly differently. And this might be a nice one. You see, we can see how those ridges form a bit of a wave that's splashing on the sides. Obviously, Pavel is not going to have a problem like this unless his boat is going very fast across the water, in which case it's barely touching the surface, like hopping, like a very fast ball hopping across the water. You might have something like that. But essentially, the most important thing is to try and have this bullet shape at the front, or teardrop shape at the front, as narrow as possible. Obviously you're lengthening your boat like that, but this is the only way to ensure that the front is always being pushed out of the water, right? So you don't have the effect that he was having. Of course, there are other boat designs like this one here, where the water is being pushed out in a slightly different way. But in this boat, the CG plays a very big role, and you see how most of the weight is concentrated towards the back of the boat, and the front of the boat is as light as possible. So this part is being pushed out as much as possible, and that will definitely help. Okay, so anyway, I hope you found this video useful. I hope that Pavel has found this video useful, and if you are intending to build um, something like an INAV boat that you want to go at a higher speed than like some very, very slow cruising speed, then this is something that you could look into, and I think that it would be quite interesting if anybody does this. I would love to do this at some point once I get my 3D printer working again, and I might look into doing something like this myself and try and improve on Pawel's project and put those files on Thingiverse and stuff like that. But for now, I hope that the advice was useful and that Pawel from FPV University might learn a thing or two about boats from somebody else. So yeah, I hope you enjoyed the video and thanks for watching.